Welcome to Code Report. I'm your host, Connor Hoekstra. I wanted to announce a more formal schedule for this YouTube channel. So along with the weekly episodes that I've been releasing on Sundays, I'm going to be releasing once every 2 weeks on Fridays an STL algorithm video. I've been releasing them in the past, but I want a more formal release schedule to get through all the algorithms as many of you have been requesting them. And as well, on every Wednesday for the next 2 years, every week, I will be releasing a solution video to one of the HackerRank dynamic programming problems. So many of you, as you can see here, have been requesting solutions to dynamic programming problems. So I'll start with the easy ones and over the next 2 years work up to the harder ones. Last week we had 7 contests, starting with round 507 on Wednesday from Codeforces. We also had round 508 on Thursday from Codeforces as well. And the third contest from Codeforces was Educational 50 that took place on Friday. As well as on Friday, we had the start of the Code Chef Long Challenge that will continue to go on next week. And we had the start of the 2-day HackerRank University CodeSprint 5 contest. And on Saturday, we had the September Easy contest from HackerEarth. And of course, we had the weekly LeetCode contest number 101 on Saturday evening. Taking a look at the top 10 leaderboards, the individual to place on multiple top 10 leaderboards was I Love Tanya Ramanova. That was the only individual to place on multiple top 10s, but we had some other big names. Notably, in Division 1 of round 507, we had Umnik in first, Kson48 in fourth, and Petra in ninth. In the round 508 contest, we had MJ Hun in fourth, Natsugiri in eighth, and KMJP in 10th. And in the Educational 50 contest, we had in first Eddie1021, in second B Mary, and in seventh Dream Moon. Continuing to take a look at the top 10 leaderboards, here they are for the HackerEarth, LeetCode, and HackerRank contests. The most notable finishes here were the top places in the LeetCode and HackerRank contests. We had Yui in first place for LeetCode and Tourist, aka Gennady, in first place for the HackerRank contest. And taking a look at the overall updated Codeforces leaderboard, we had no changes in the top 2, but we had Umnik jumping up 2 spots due to his first place finish in the round 507. Silo Viali dropped 1 spot. LHIC jumped back up into the top 10. Petra dropped 2. Bank is still ranked at number 7. KO Osaga dropped 2 spots. Swisstock dropped 1 spot to 9th, and Dodoria also jumped back into the top 10. In today's video, we're going to be covering the solution to problem 3 from the HackerRank University CodeSprint 5 problem AB special points. The problem states, consider a simple undirected graph G with a vertex V and 2 positive integers AB. Let ADJV denote the number of vertices adjacent to V. We say a vertex U is reachable from V if there exists a path in G from U to V. We say V is AB special if there exists U and U prime reachable from V such that A times ADJU is less than ADJV is less than B times ADJU prime. It is not required that U and U prime are distinct from V. Given a graph G, how many of its points are AB special? And then it gives the restraints below, notably that the number of vertices that we're going to have are going to be between 3 times 10 to the 5th. So what we note from this is that we're probably going to need something better than quadratic, so either n log n or linear. So this problem statement is extremely confusing. It took me a while to understand it. So let's try and break down what they mean by this ADJV and this sort of formula here and what the problem is actually asking for. So we'll do that by taking a look at one of the examples that HackerRank gave us. So here is the input for one of the examples. The 2 first integers here, 6 and 5, represent the number of vertices and the number of edges, and then the M lines here, the 5 lines here, represent the edges between two vertices, note that they're undirected, so you can go from 1 to 2 and 2 to 1. And the two values here are A and B, which are going to get plugged into our formula to see what vertices satisfy that. So if we look at this visually, it looks as follows. It's just a straight line with edges between each of the vertices here. And so we're given A is equal to 1 and B is equal to 2. So the question asks how many vertices in our graph satisfy the following formula. So the first thing to note is that as I sort of talked through the problem statement, this really means A times, this value and B times this value. So that makes it slightly more clear. And then what is ADJ U slash V slash U prime? So it states in the problem, let ADJ V denote the number of vertices adjacent to V. So this is just a really fancy way of representing for each vertex how many neighboring vertices are there. So we can basically just set up a little row here, and for each one of our vertices, you can see here that the ones at our ends, they only have one neighbor, obviously, but then the ones in the middle, they have two neighbors, one on the left and one on the right. And that's basically all this ADJ U slash V means. So the notation that I'm going to use is I'm going to switch it up a little bit and just have it as, whatever you're using to represent your vertex. So here I'm using V in the formula here to denote that we have two different vertices, U and U prime. I'm just using that. And then subscript E just means number of edges. So in the problem it states that we know that the number of, or the edges are distinct. So you're not going to have multiple edges from 1 to 2. There's only going to be one. So the number of neighboring vertices is also going to be the same as the number of edges leaving from your vertex. So we can just use this notation. And so now we've sort of reduced our problem to asking what or how many of the vertices in our graph satisfy this formula here. So we just plug our A and B in, and once we do that, the sort of A will disappear because it's 1, and then we have the B here, which is 2. And it's going to basically say that, is there for each vertex, so if we're looking at our second vertex here, we would plug 2 into our VE. Can we find a node that has less than our 2 edges here and then greater than 2 times the number of edges of our other node? And the problem states that the 1, 2 special vertices are 2, 3, 4, and 5. All these vertices are adjacent to 2 other points, and 1 is reachable from each of them, the 1 being this vertex. Since 1 is only adjacent to 1 point, we have the lower bound being set, we have the lower bound by letting U be 1, and for the upper bound, we can choose U prime as 2 for all points. So basically, what they're saying is that we can set the lower bound of this equation to 1 because every single one of the vertices in this graph can reach this node. So that's going to be our minimum, because we want to find our minimum value in our graph to put on the left, and we want to find our maximum value in our graph to put on the right. And so what this ends up with is we have the following 4 nodes being 1, 2 special, because we can plug the value of the number of edges for 1 here, and then we can choose any one of these middle graphs to plug in here. And so we just end up with this formula, 1 less than the number of edges for a vertex less than 4. And so the question is just asking how many values in this sort of VE row satisfy this equation, and we can clearly see that the ones in the middle here satisfy this. And the only reason that the ones on the end don't is because they only have 1 edge. So when we plug 1 in here, clearly 1 is not less than 1. So once you look at the problem and you understand it, it's actually not that difficult. So basically all we need to do is figure out for each vertex how many edges or sort of neighboring vertices are there. And if you know anything about graph theory, we can simply accomplish this just by creating an adjacency list. So an adjacency list is just a simple data structure, typically a vector of vectors, and each vector represents the neighbors for the corresponding vertex. So you can see here for our vertex 1, the only neighbor it has is 2. And then for 2, the neighbors it has is 1 and 3. And so just by looping through this, we can see that the size of our inner vector corresponds to the number of neighbors that this vertex has. So just by creating our adjacency list, which we can do in linear time, we already have the number of neighboring vertices for each vertex. And as well, we can also derive the number of minimum neighbors for a given node in our graph and the number of maximum neighbors for a given node in our graph, which is clearly going to be 2 and 1. So we can do that in linear time just by looping through and figuring out sort of what U prime will be and U will be, and then plugging that in here. So if you do that, you basically have most of your solution. And if you submit at this point, you would end up with the following. So you'd get a 7.64 just by creating your adjacency list, figuring out the min and max of edges for your given vertices, and then just looping through, and for each one of your vertices, checking does it satisfy this equation. So why is it failing in some cases? And the answer to this is that we're not going to necessarily just have one connected component. So what that means is that we could have a graph where we have multiple connected components. So if these were trees, you would call this a forest. So a graph that has multiple trees in it is called a forest. These aren't technically trees. So this is just a graph that has multiple connected components. And so what that means is that we can't just simply go through our adjacency list and find the node that has minimum edges and the node that has maximum edges and then store that and plug each of our sort of vertices into this formula. We have to do it on a connected component basis. So for each connected component, we have to figure out the minimum number of edges for a given node and the maximum, and then do that sort of process for each connected component. So this only complicates the problem a little bit. Basically, we're doing the exact same thing, but we have to store the min max for each connected component, and we need to figure out how many connected components there are. So this is actually pretty straightforward. We can figure out how many connected components we have by just setting up a vector and then doing a depth first search. You can also use BFS or an algorithm called quick union, but those are slightly more complicated to implement. You can do a DFS in literally a couple lines. And then once we have the connected components, we're just going to loop through, and in a hash map, we're going to store the min and the max of our edges for each of our connected components. And so for this problem, we would end up having a solution of 2 instead of 4 because the values here we're going to get if we plug in our A and B's and our min and max, we still have 1 less than VE less than 4 on our left here, but on the right, this is actually a mistake. It should say 1 or no, this is correct. 1 less than VE less than 2, but when we plug in our VEs, we always have 1 less than 1, which is false, so neither of these qualify. So when we break this down, in order to solve this problem, this is what we have to do. Step 1, create an adjacency list. Step 2, determine our components using either DFS, BFS, or quick union. We're going to use DFS in my solution. And then in step 3, determine the min-max edges for a node in each component. And then once we've done all this, we just need to go through and count the vertices that satisfy our formula. So hopefully this made sense and cleared up what the problem was asking for. If it doesn't, hopefully by looking at the code, you'll be able to understand what we're getting at here. So let's take a look at our code. So here's our main function, int solve. Note, we're using a couple type aliases throughout the solution. So VVI stands for a vector of integers, a VI stands for vector of integers, and LL just stands for long, which you need to use in order to avoid integer overflow. And so if we come back here, you can see pretty clearly what we're doing. So we're first setting up our adjacency list, then we're determining the number of components, and then we're finding the min-max edges for each of our components. And then we're setting up this generic lambda here. And basically you can see on the last line that we're just returning true or false based on whether or not for our given vertex that we're looking at, it satisfies this equation. So a times p dot second less than v underscore e. V underscore e is the number of edges of our current vertex. We do that just by looking at the size of our current vector. And then v underscore e less than b times p first. So what is p? It's just a pair that represents the min and max of our given component. So m here is our hash map storing our min max. It's unfortunate that we only have C++14 on HackerRank. If we had C++17, we could use structured bindings and we could make this even read that much more clear by sort of destructuring our first and second into max and min, and then we could just read this as follows. So once we have this generic lambda, we can pass it into our count if function and just loop through our adjacency list, and this is going to pass in for each of our inner vectors that vector here, and that's how we get the number of edges. So it's just the size of that inner vector, and then we need to get the min and max of our component that this vertex lives in, and then this will compute the number of vertices in our graph that meet this sort of condition stated in our problem. So let's take a look at the functions that are defined at the top here. So create adjacency list. So this one's pretty straightforward. We're just declaring a vector of integers. So each inner vector is going to represent the number of edges that are reachable from our current vertex. And so you can see we're just taking the edges vector of vectors that's given in the problem, and then we're doing -1 on each of the values because we want to have 0 indexed arrays, and then just pushing back into the corresponding vertex. If we take a look at the next function, determine components, here we're just setting up a vector of integers representing which component for each vertex, and we're initializing them all to -1, and then for each of these we just call a simple DFS. So once you've made one call, it's going to go and explore every single vertex that's reachable from that component, and so at the top of this DFS function we just need to make sure that we only explore vertices that haven't been explored so far. If this is the case, we set the group or the component of our current vertex that we're at to be equal to the current component that we're exploring, and then we just do our DFS call. So for each of the nodes that you can reach from the current vertex, call DFS again. And once we've finished doing this for all of our elements in our adjacency list, we can just return our vector, which is going to now represent our components. So in our second example, we're going to end up, like the second visual example that we looked at, you're going to end up with 0, 0, 0, 0 for the first 4 vertices, and then like 4, 4 for the second 2 vertices, which is going to represent sort of just 2 distinct group IDs for our components. Then taking a look at our last function, this is the find min-max edges. So at the top here, we're just declaring a hash map where the key is going to be sort of the group ID or the component ID, and then the value is going to be a pair of long longs which represent the minimum and the maximum number of edges for a given node in our component with the ID that is the key. So the first thing we're going to do is we're just going to loop through our components, and we're going to insert into our hash map sort of an initial pair where we're setting the value of our maximum to be 0 and the value of our minimum to be n. So those are the initial values of our max and min. And then we're just going to loop through and check for each of our basically pairs that if we have a node that either has more or less than our given minimum or maximum, we're setting that based on the number of edges for our given vertex. So you can see here that basically what we're doing is we're getting the corresponding min and max from our hash map based on the component ID. So once we do that, we basically have our hash map that for each component stores the minimum and maximum edges for a given node.
And so that is all the code. So we come back to our whole solution here, and this will get you full marks. So it's actually a pretty straightforward problem. There's just a bunch of small parts. So creating the adjacency list isn't too difficult. Finding the number of components is not too difficult. And finding the min-max edges for a given component isn't too tricky either. It's more just putting them all together and seeing what needs to be done in order to solve this problem. So the last thing to talk about is the time complexity, which is going to be linear because each of these steps is linear. Adjacency list is linear, determining components. The DFS is linear because you only visit each vertex once. Find min-max edges, you're just looping over your adjacency list, so that's going to be linear. And then our countif function is also linear as well. And just to note, make sure that if you're testing this code or writing similar code that you use the C++ 14 compiler language option on HackerRank, because we're using generic lambdas and also function deduced return type, which are both C++ 14 features. And note that you can't use the structure bindings here. You have to go back to using the autoref_p, because this is not supported yet in C++ 14 and / on HackerRank. Taking a look at the contests happening next week, we have from Hacker Earth on Saturday the Hour Storm number 3 contest. Of course, we also have the weekly Leak Code contest number 102, and on Sunday from Code Forces we have round 509. And throughout the week we will also continue to have from Code Chef the September Long Challenge.
As always, if you enjoyed this video and found it helpful, hit that like button. If you want to see more, make sure to hit that subscribe button. You can follow me on Twitter for reminders 30 minutes before contests start, and you can find all of the code shown in my videos on my GitHub page. Thanks for watching, and I'll see you in the next video.